Stripping down science. The Naked Scientists.
Hello and welcome to The Naked Scientists this week with me, Chris Smith, and also here this week is Helen Scales. Hi, Helen.
Hi, Chris.
Now, this week, how long is your index finger compared with your ring finger? Because scientists think that it could be used to tell us how good we're going to be when we're children, subsequently that is, at maths and languages. Also, how ants have mastered the art of road repairs and also bridge building. And is this the biggest geyser in the galaxy? Scientists now think they understand what powers a jet of water that shoots, get this, 500 miles into space from the surface of one of Saturn's moons. All that's on the way. Helen.
Also this week, we're venturing out to the final frontier to catch up with space scientist Maggie Turnbull, who's probing the galaxy for planets like Earth and looking for signs of intelligent life. So stay tuned to find out what she's found so far. We'll also be talking with astronomer Carolyn Crawford to find out what space is actually made of, how galaxies are formed, and why the universe is said to be getting bigger. Plus, in Kitchen Science, we'll be showing you how to measure the speed of light with just some bread and butter and a microwave.
So we do absolutely need your space questions for Maggie and Carolyn. I'll give you the contact numbers in just a second, but first, here's this week's teaser. You can win yourself a signed copy of our book, which is Naked Science. It's jam-packed with interesting science discoveries. The contents, I guarantee, will brighten up even the dullest dinner party. If you want to win a copy, what we want to know is how fast is the Earth travelling around the Sun? And the person with the closest answer will win.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
So this week we've had some bizarre news of instant road repair in the world of the ants. It seems that some types of ants are prepared to get walked all over to let their fellow ants bring home the food. A team of scientists led by Scott Powell from the University of Bristol here in the UK have been studying huge swarms of up to 200,000 army ants in the rainforests of Panama. And as they go in search of food, they see that some of the ants use their bodies to plug up potholes in the path of the swarm, allowing other ants to walk easily over them. Now, to test exactly what was going on, the researchers brought a colony of ants into the laboratory and offered them planks to walk across with different sized holes drilled in them. And they discovered that the ants select holes to exactly fit their body size.
What, with just one ant or several ants nose to tail across the holes?
It can either be, well, basically what happens when an ant encounters a hole in their path, they walk around it, size it up, and if they think they're about the right size, they climb in and block it up.
But life's not like that, is it? It's not always going to be a world full of holes that are ant-sized conveniently, is it?
Well,
so what do they do when the holes don't match?
If they're really big, then they do collaborate as well and make sure that they fit in. But I think it's either one for you, or if it's a really big hole, then they'll all come in together and figure that out. But they can vary in length quite a lot, from about 2 millimetres to a centimetre, which is about 0.4 of an inch. So, you know, they can be quite big. But anyway, once they're in place and the living floor, can stay put for hours on end while thousands of other ants walk over them. And the researchers found that when ants used themselves to plug up the holes like this, the colony was much more efficient at collecting food, basically because they can move much more quickly. They actually speed up and down a lot more quickly than if they had to go around all the holes and kind of... You can imagine if you were driving your car, if you've got to sort of miss all the potholes, you don't go very fast, but if you can just zoom straight over, it would be
So how do
great.
they decide who gets the unlucky job of being walked on then?
Well, it's these worker ants who, it's all clones, it's all part of a big colony, you know, and they're not the ones that actually reproduce, these wonderful social insects that do behave in such odd ways. But I don't know, I mean, apparently if they think, they're too small, and they do carry on and wait for another ant behind to fill up the hole. But I think it's wonderful. Can we have something like that for our roads? Can we get the ants to fill up the holes in our roads?
It puts a whole new meaning on being walked all over, doesn't it?
Absolutely.
Now, Helen, how big is your index finger relative to your ring finger?
So my ring finger actually looks quite a lot, in both hands, quite a lot longer than my index finger. What do you think?
OK. Well, we've got Carolyn Crawford here in the studio. Let's just poll her too. Carolyn, which is your biggest? Ring finger or index finger?
Oh, the ring finger's definitely longer.
Well, that kind of fits because there's a guy who's based at the University of Bath. His name's Dr. Mark Brosnan. I don't know if he's related to James Bond. But what they're interested in is how the ring finger relates in length to the index finger, because in the past, when people have made these measurements, they've found that people who've got a very long index finger tend to be more often men than women, and they tend to be much better at sport, and they're also much more likely to get into a fight at an ice hockey match. That's the research they've done so far. But the point is, what this is showing, they think, is a sort of index of maleness, or how much testosterone you probably got exposed to when you were developing as a baby inside your mum. So what Mark Brosnan's done is to say, well, can we actually map this physical marker onto how the brain works and how it develops in young people. So what they did was got 75 school children, and they photocopied their hands, and then they made measurements of those photocopies to work out the ratios between the ring finger and the index finger length. And then what they did was to go to their SATs, the standardised assessment test that all kids of a young age go through now, and they should be the same test for everyone, so it should be a fair test. And they then compared the SAT test results, which are looking at how good you are at maths and how good you are at languages, and comparing that with this ratio of how long your index finger is to your ring finger. And what they found was that in boys, you tend to have a much longer index finger to ring finger ratio, and that mapped onto a better performance in maths and numerical skills and spatial awareness. And if you had a longer ring finger, you tended to be better at languages. And what they think is that estrogen makes your ring finger longer. That's why women tend to be better at languages, and testosterone makes your index finger longer, and that's why you tend to be more aggressive.
Did they actually test this in girls as well, or was it just boys?
It was boys and girls who were looked at.
Right.
Yep.
There you go. So have a look at your fingers, and it might give you a hint at what you're good at.
Well, they're not. He actually says, we're not looking to replace. We're not suggesting that finger length measurements could replace SATs. He says, but finger ratios provide us with an interesting insight into our innate abilities in key cognitive areas.
Very interesting indeed. Excellent. Well, back in 2001, we had a rather far-fetched story that hit the headlines, declaring that a baby shark had been born in an aquarium tank to a virgin female shark, and it turns out the Immaculate Conception did actually happen. This miraculous birth of the bonnet-head shark, which is a close relative of the hammerhead shark, which you might be able to pick out with its weird-shaped head, it took place in Henry Dorley Zoo in Nebraska in the United States. And until now, scientists thought that this unlikely sex-free birth was probably a consequence of the females storing up sperm from their time in the wild, which was about 3 years before they came into the aquarium.
Can they do that? Can they store sperm for that long?
Well, I don't think we know that sharks can definitely do that. Lots of other animals can. Kangaroos can keep embryos for years and years, sort of stasis, if you like, and then bring them out when they want to actually have another baby. And amazing things like that go on. But now what we know, 6 years later, after this genetic study that's just come out from a team of American and Irish scientists, has confirmed that it is indeed an immaculate conception. It's a process known scientifically as parthenogenesis. And instead of needing sperm from a male to fertilise their eggs, some females can actually produce embryos without having sex at all.
They just switch on their egg to begin to divide without the sperm giving it a second set of chromosomes.
There's various different processes. This one is actually one in which there's another body called a sister polar body, which is produced during egg production, and that fuses with an egg and produces a viable embryo. And that's how
presumably,
it
is it a clone of its mother?
It is.
Then?
That's right. That's how they discuss. That's the genetics, the link. It had no male genetic material in it, this baby, and it was in fact identical. Well, the bits of DNA that it had were identical to one of the females, because one of the key points actually in this is it's a wonderful story, and it's an incredible discovery that this incredibly ancient group of animals, sharks, have been around for 450 million years. To know that they are able to have this process of asexual reproduction is amazing. But it's also quite worrying, because the baby shark produced by this way has much less genetic diversity than its parent did. The process that happens here means they have much lower genetic diversity, which means they're actually much less well equipped to survive in the wild. So perhaps if we were to make male sharks in the wild much more scarce by overfishing them, because they tend to be the bigger ones, then females might start just relying on this asexual reproduction, and then ultimately populations of sharks could lose that genetic variability, which is very important for their survival. We don't know really what will be happening if we were doing that. So
the London Zoo, just before Christmas, had the world's first sort of immaculate conception in a Komodo dragon.
Yep.
These are these massive lizards.
You see it in all sorts of animals,
that was
actually
interesting, because they realised that these animals probably have this ability, because if you are washed up on a beach and you've got just one female, if you can do this, then evolutionarily it's beneficial, because you could repopulate the island. And the reason they say that is because when a female has this parthenogenesis, the egg switches itself back on. The product of that is a male Komodo dragon, because in Komodo dragons, unlike females where 2 X chromosomes make you female, in a Komodo dragon they have, I think it's 2 W chromosomes. If you have 2 of those, then you're male. So what you get is a new male formed, and then you've got a male and a female, and you can have normal sex again and potentially make that genetic diversity come back. So isn't nature a wonderful thing?
Absolutely, indeed.
It is The Naked Scientists with Chris and Helen. This week we're talking about space science, and if you have any questions, we'll be joined shortly by Carolyn Crawford from the University of Cambridge. She's waiting in the wings to take your questions about the birth of the universe, how galaxies form, why they're the size they are, and why they're the shape they are, how stars work, how planets form, that kind of thing. If you've got any questions for her, number on the way shortly. We're also going to be talking to Maggie Turnbull, who's looking for extraterrestrial life. She's looking for planets a bit like the Earth, how is she doing it, and what she found. That's all on the way. And also, don't forget our teaser this week, up for grabs, a copy of Naked Science, which is our book. We're going to sign it, which will put the value up by at least treble the price, so you can flog it on eBay. It's worth 3p instead of 1p. We want to know, how fast is the Earth travelling around the Sun? The person with the closest answer is going to win.
The Naked Scientists, supported by the Wellcome Trust.
Well, we're beginning our tour of the universe now with a trip to Saturn and one of its tiny moons, which is called Enceladus. Now, when the Cassini spacecraft flew there in 2005, researchers noticed that there were some very strange hotspots around the south pole of this tiny moon, and they now discovered that these hotspots actually give rise to a gigantic geyser, and it erupts regularly, a bit like Old Faithful here on Earth. But the geyser on Enceladus is on a totally different scale entirely, because when it erupts, it sends enough material out into the air of that tiny moon to make it all the way out into space and even join up and make some of Saturn's famous rings. And one of the researchers who's been looking at the phenomenon is NASA's Terry Herford, and he joins us now. Hi, Terry.
Hi, thanks for having me.
Thank you for joining us. So what powers this beast that you've seen on Enceladus?
Well, there's some question about what the heat source is. Enceladus is so small that it should have cooled off a long time ago. But something has kept this moon warm, and it's most likely tidal friction. Because of its orbit, it's constantly reshaping itself, and the reshaping dissipates heat internally through friction, and that probably ultimately powers the geysers. So how does that actual heating process work? Why should just orbiting a planet make this moon warm? Well, if it were in a circular orbit, it probably wouldn't be warm. But it's in an orbit that's not completely circular. And so because it's not circular, the distance to Saturn is changing constantly, and the position of Saturn in the sky is changing. And so this constantly causes the body to reshape itself. And in the process of reshaping itself, it dissipates heat. So it's a bit like rubbing your two hands together and you get some warmth between them. Right. So when that happens, how does that give rise to this phenomenal 500-mile-high jet of water on the south pole of this moon? Well, when in the process of warming itself, it can create some liquid water in the South Pole, and when that liquid water is exposed to the vacuum of space, it can then erupt at speeds that allow it to then escape the surface. And because the body is so small, it doesn't take very much velocity to actually get things off the body and into orbit around Saturn. And why is it only the South Pole, then, that's giving rise to this phenomenon? Why don't we see these things spurting out all over this moon? Because it must be getting tugged and squashed all over the place. That's a good question, too. In the process of heating the body, some of the material is warmer, and that material has a lower density, and it causes the whole body to reorient itself so that warmer area is located at one of the poles, either the North Pole or the South Pole. In this case, it just happened to go to the South Pole. And what does this tell you? Because obviously you're now studying this using Cassini. What does this tell you about what the structure of that moon must be? Is there presumably a big source of liquid water underneath then somewhere? And could there be life in there even? Yeah, the work that I've done is looking at the stresses in the South Pole and seeing when the features in that location open and close because of the tides. The tidal stresses pull open some of the fractures, and when it pulls open the fracture, it then allows the liquid water to be exposed and allows the eruptions to occur. In order for the stresses to be high enough to do this, I speculate that there's got to be a global ocean of water underneath an icy crust, similar to Europa, a moon of Jupiter. And so if you've got liquid water and it's warm enough to give rise to a sort of geyser phenomenon, that suggests that you could end up with similar situations that you've got here on Earth around hydrothermal vents, so you could see life there. Right. That makes it a very interesting place to look for microbial life or some sort of simple life forms. And so how are you going to get to the bottom of that? Because it's obviously not convenient to take about 3 million mile trip to go and drop by Saturn and take samples. Is there a way to answer that question simply? Well, the fact that we have the geysers erupting means that liquid water is somehow getting up to the surface and ultimately into space. So you may not have to actually land something on Enceladus to look and see what kind of things are inside the water, since it's being transported to you. And it's much more convenient on Enceladus to look for this than on Europa, because Europa has a very thick ice shell, and it would be very hard to get to the liquid water underneath it, whereas Enceladus may not be as thick, and of course the water is getting right up to the surface. Thanks, Terry. Terry Herford from NASA Goddard over in the States, who's been studying Enceladus, which is this tiny moon right up against Saturn with this phenomenal
geyser phenomenon happening on its surface. Helen.
You're listening to The Naked Scientists, and of course we have waiting in the wings Maggie Turnbull, who'll be telling us all about what she's found out about extraterrestrial life. And here in the studio we have astronomer Caroline Crawford, who's waiting to answer your questions on galactic interstellar science, anything like that.
Now, as you know, at The Naked Scientists we try and tackle all your burning science questions, but sometimes you ask something really rather difficult, and we're really rather stuck for an answer. So we've got a new feature coming out on The Naked Scientist. It's going to start next week, and to tell us more about it, here's Sabina Mignovich.
Thank you. Yes, we've got a brilliant new feature launching on the show next week, and it's called Question of the Week. Now, the aim of this is to answer your more complicated scientific questions, and to do this, each week I'll be taking a puzzling problem and finding a knowledgeable expert to explain the solution. So if you have a quirky query you'd like me to solve, send me an email to questionoftheweek@thenakedscientist.com. Also, I'll let you know a week in advance what the problem is that I'm trying to solve. That way, if you think you know the answer, you can drop me a line to let me know. The best solutions I receive will be read out during the following week's show, along with the expert answer. Next week, I'll be trying to solve this problem.
I'm Brian from Norwich. A question that's been bugging me for quite a number of years is to do with gravity, actually. If I'm standing in Australia and I drop a stone and it hits the ground, if I stand in England and I do the same thing, the stone drops to the ground. Now, if it was possible to drill a hole straight through the earth from one side to the other, would those two stones meet in the middle and then float?
If you think you know what would happen if you drop something into a hole through the earth, or you have a question of your own, then get in touch by sending an email to questionoftheweek@thenakedscientist.com. Tune in next time for the launch of Question of the Week. But now, back to the studio.
Thank you, Sabina. So if you've got a science question that needs a bit of expert attention, then email it to us, questionoftheweek@nakedscientist.com. Quick email here from Akshay Rao, who says he's listening in New Delhi in India. Been listening to your podcast for a month now. I've not been able to get through all of the archives yet, but you guys have me hooked already. I'm an undergraduate computer science engineering student, and I often listen to the podcast while I'm travelling to and from my students' homes, where I give them guitar lessons. You guys are doing a great job. Thank you very much. It's amazing to think that people in India on their commute are listening to what's going on here in Cambridge.
It really is wonderful. It makes the world seem like a very small and intimate place indeed. I've got an email here from Don in Castro Valley in California, and he says, TV crime programmes are fond of showing DNA samples taken from suspects by swabbing the inside of their mouth. Now, human mouths are filled with all sorts of bacteria, so the swab must collect piles of non-human DNA, as well as perhaps a bit of cow and lettuce DNA or tuna or whatever you've had for lunch. So he wants to know, how can human DNA be separated from all this other gunk that might be swirling around our mouths, assuming we haven't just cleaned our teeth? And he says, thanks for the great programme.
Yeah, the answer is that, yes, the DNA samples you pick up from the environment are contaminated with everything, bacteria, what you've had for lunch, doesn't matter where you get it from, you're going to have bacterial and other kinds of contaminating DNA. But the way we do the technique is that we amplify human DNA sequences, and then we use a probe, which is a little piece of genetic material that only latches on to very specific sequences of DNA, and we use probes that only recognise human DNA sequences, and you then bind that onto the DNA sample you've collected, so the only patterns you see relate to human DNA that you've got from a crime scene. So even though there's all that other spurious DNA there, it doesn't matter because it doesn't mix up or interfere with the process.
We're actually just looking for human DNA, really. We're kind of ignoring anything else that might be out there. Excellent. Well, now time once again to go stateside and we shall join Bob and Chelsea for this week's Science Update.
This week for The Naked Scientist, we're going to talk about new research on diseases of the brain. I'll report on what scientists are learning about the connection between schizophrenia and depression. But first, Chelsea has this story about a surprising new diagnostic tool.
In the future, neurologists may stockpile canisters of nasty odors like those of pungent cheese, rotten meat, or skunk. They'd be used to screen for degenerative brain diseases like Alzheimer's. University of Cincinnati psychologist Robert Frank says the sense of smell is often a first casualty of these diseases, so he and biologist Robert Gesteland invented a simple sniff test.
And it's all based on the observation that if you're sniffing and you don't encounter a smell, you take bigger sniffs than when you're sniffing and you do encounter a smell.
Their device measures the air pressure created by a sniff and compares how hard a patient sniffs at a strong odor versus an empty canister. They use all kinds of smells, but Frank says unpleasant odors are especially useful.
If you just reflect on your experience in life and imagine yourself testing the milk for whether it's sour or entering into a a public restroom that's particularly odoriferous, you can appreciate that those kinds of smells are very effective at suppressing your desire to sniff.
If the patient sniffs just as hard at odors like that as he does at any empty canister, further testing would determine whether it's a result of nasal problems, simple aging, or the start of more serious brain damage.
Thanks, Chelsea. Schizophrenia and mood disorders like depression tend to run in the same families. A recent report in the journal Neuron shows how different kinds of damage to a single gene called DISC1 may lead to one illness or the other. The researchers bred 2 strains of mice, each with a different type of DISC1 damage. According to medical geneticist David Porteous at the University of Edinburgh in Scotland, the 2 strains developed very different symptoms.
So that we had, on the one hand, mice that were hyperexcitable and unable to mask out auditory stimulation, and on the other hand, we had mice that were behaving as if they had a depressed mood and low sociability.
They then tested the mice on different types of psychiatric drugs.
The ones with the more schizophrenia-like behavior responded positively to the treatment with the antipsychotic, and those with the mood disorder responded to the treatment with an antidepressant.
It's not yet known what causes the damage, when it happens, or how each type of damage leads to such different symptoms, but it's hoped that solving these mysteries will help doctors spot the illnesses earlier and treat them more effectively.
Thanks, Bob. Next time we'll tell you how physicists are combining diamonds and lasers to simulate the insides of giant planets. Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Thanks, guys. Now, we're always talking about how the Americans love our English accents, but I love the way you said Edinburgh. Well, we say Edinburgh. More from Bob and Chelsea next week, and you can find out more at scienceupdate.com.
So Naked Scientists with Chris and with Helen. In a second, we're going to be talking with astronomer and space scientist Caroline Crawford from the University of Cambridge.
Right, and we've got the teaser question as well, so we want your answers to how fast is the Earth travelling around the Sun. We've had some great answers. Keith in Suffolk, a bit low, maybe try a little bit higher. Simba, you are definitely too low. Need to try a bit more. Thank you so much, Liz in Bar Hill, who's haggling over miles per
Just
hour.
changed her answer by 1 mile an hour.
Which, I'll give you a little hint. It's a lot more than a few miles an hour. But thank you for your answers. Keep them coming in. And we will be announcing the winner later on in the show.
So how fast is the Earth whizzing round the Sun on its orbit in miles per hour? What do you reckon the answer to that is?
Laying the facts bare, the Naked Scientists.
It's The Naked Scientists with Chris and Helen, and we're talking with Caroline Crawford from Cambridge University. Caroline, hi, welcome to the programme.
Hi.
Great to have you with us. Now, a lot of people probably look up into the void of space, and it's pretty large, and they're thinking, how did all this get here? And also, when I look up there and see blackness, what actually is that? So what is the fabric of space?
Oh, good. Straight for the deep question. What is the fabric of space? Well, there's so much in space. There's stars, there's planets, there's galaxies, and all of this started right at the point of the Big Bang. So, I mean, all of it starts there and it expands outwards and it's all devolved into all these wonderful things we see. So,
but is space a vacuum? I mean, is it some kind of material that we refer to as a fairly, sort of without committing ourselves, as the ether or something, or is it just nothing? What actually is space?
Well, space is never truly a vacuum. Even you have these enormous voids in space, and even those might still have a few particles in. But generally, in terms of what we're used to, we regard it as a vacuum. But that's in the enormous spaces between the stars and between the dust and gas clouds and the galaxies.
So when you say that everything started with the Big Bang, that was about, 14 billion years ago, sorry?
13.7 thousand million years ago.
That's a very precise answer.
Oh, yes, I looked it up before I came in.
But how do we know that that's when it happened?
Well, we can track the motions of the galaxies. They're all expanding outwards after this initial explosion, and we can work out how long they've taken to get there, travelling at that speed, and you backtrack it, and you find that they all came together about 13.7 thousand million years ago.
So when you say galaxies, can you just define actually what is a galaxy versus the Big Bang, and how did they come into being?
Oh, right. Galaxies are giant aggregations of stars. So something like our own galaxy, you've got maybe about 100,000 million stars all held together by gravity. And galaxies come in shapes that are like frisbees, or they come in shapes like footballs or rugby balls. And they're just big collections of stars all held together. Now, all of these are scattered throughout the universe.
But why would they form a galaxy? Why would they cluster together in there? Why wouldn't they, for instance, just spread out? If you've got something that kicks out in a massive great explosion like we think the Big Bang was, why not just shower everywhere with material? What causes it to begin to come together in that way?
It's because the universe was never exactly the same density throughout. Even in these very early stages before, or just after the Big Bang, the very early stages, there are some bits that are just slightly more dense than others. And as you know, if there's more matter, it's got more gravity, it pulls more matter towards it. And, you can regard these as the seeds, which kind of pull stuff together, and it starts to accumulate things that are then going to grow into the galaxies we see today.
Why are they different sizes and shapes? Why not just end up with them having a sort of fairly consistent size and aggregation like that? Because they have different structures, don't they, galaxies?
Yeah, they've got different structures, and the key thing might be whether they formed near another galaxy, whether you've got two galaxies forming in the same area, whether they formed in isolation, whether the gas cloud was originally spinning. Things that are spinning tend to condense down into flat disks, so that maybe is how you get a spiral galaxy as opposed to these kind of ball-shaped ones, which maybe came from a much more static cloud.
Because Andrew Gaspar's emailed us and says, I understand there are two types of galaxies. Some have these spiral arms and others are an elliptical shape.
That's right.
So what processes would form those two different types?
Well, we think with galaxy formation, everything's very hot after the Big Bangs. You start off with this enormous cloud of very hot gas that begins to cool. And as gas cools, it starts off radiating X-rays, and it cools down, and eventually it condenses down into the stars that form the galaxy. And so, if you have a very big cloud of gas that's quite static, maybe it goes down to the elliptical-shaped galaxy. But imagine it's rotating ever so slightly. The things that condense from it tend to be this kind of disc shape, the more sort of these spiral-shaped galaxies like we think our Milky Way is.
What's at the middle of our galaxy that keeps us all spinning around it?
Well, I'm calling it a frisbee shape. In truth, the analogy we tend to use is it's like two fried eggs stuck back to back. The frisbee is the white egg of the fried egg analogy, and there's this yolk in the middle, which is a big ball of stars. There's a massive ball of stars in the middle, and then there's this disc spreading outwards. So there's a big ball of stars, and right at the centre of that, there's a supermassive black hole.
Presumably we can't see it. Is that inferred that there must be something big and heavy there? Is that what's attracting everything and holding the galaxy in the shape that it's got then?
Well, no, it's not. I'm just telling you what's in the centre of our galaxy. It's not the supermassive black hole that's keeping everything glued together into the galaxy. To go back to the first question, we know it's there because it affects the motions of stars close to it. So if we track out the motions of stars, we can see they're responding to a mass that's about 3 million times the mass of our sun within a tiny, tiny volume. And the only thing we know that could be like that is a black hole. But it's not that that's keeping the whole galaxy together. You've got the stars that we see in the bulge and in the disk, and of course there's always the stuff that we don't see. There's the dark matter, and that has gravity. It doesn't radiate in any waveband, but we can know it's there again because of the motions of the stars, and that's crucial in holding our galaxy together.
Why doesn't that black hole eat the ball of stars that are around it then? Why don't they just fall into it?
Because it's probably eaten anything that came close to it. During the galaxy's been around a long time, several thousand million years. It's eaten everything within its vicinity. There are stars that come close to it and kind of orbit round it, but it's probably cleared out its immediate surroundings, and things further out, they orbit round it, but it's the gravity, they're so far away, the gravity is such that it doesn't actually pull them onto it, it just brings them to orbit round it.
Now, it's said, and I think Edwin Hubble discovered that the universe is expanding. We know that because if you look at distant objects, they seem to be going further away from us. They're so-called red-shifted. Why is it when you look at some galaxies, they appear to be coming towards us? Because if space is getting bigger, wouldn't everything be moving away from each other?
Well, on the whole, everything is moving away. Whichever galaxy you could do the measurements from, you'd find that, on the whole, all of the galaxies were moving away from you. That's the general motion of space-time moving out. This is the expanding universe. But of course, if you've got a galaxy that's actually quite close to you, you might start feeling the gravity of that galaxy. So, for example, the Milky Way is moving towards our nearest big neighbour, the Andromeda Galaxy. And even though we're both moving out as space-time expands, we're still moving towards each other. So sometimes you get these little local peculiarities where galaxies pull together under gravity, even though they're still moving outwards. So if you get things very close to you, yes, sometimes due to these little peculiarities, they can seem to be moving towards you. But in general, everything else is moving out.
Got a couple of emails for you and a text. Keith in Watford says, what determines the orbital distance from a star that planetary material will coalesce? Is that just gravity?
Oh, that's a difficult question. It also depends what your star is made of and how big it is and how much stuff there is left behind. I mean, if you have a planet that's made of gases and what we call volatiles, so something like Jupiter or Saturn, they're only really going to condense much further out from the sun because these tend to get swept out by the winds from the young star forming at the centre of the nebula that's condensing down to form the planetary system. If they're made of solid rocky material, so like our Earth, Mercury, Venus, Mars, they tend to coalesce much closer in. So it does depend what kind of planet you're forming.
Got an email here from Fred and Scott, and they say the Earth orbits the sun, non-circular orbit. If outer space is really, really cold and near to the sun is really, really hot, how close would you actually need to get to the sun in order to be at about room temperature?
Be about room temperature where? Where on the Earth?
They don't say. So I guess you've got 4 degrees of freedom, excuse the temperature-related pun, to give it an estimation as to where in space that would be.
Well, it's very difficult because obviously as you go up from the surface of the Earth, you're going to get cooler. And if you're on the night side of the Earth away from the sunlight, it's going to be different from the day side. I think it's actually quite a difficult question to answer. There are lots of different ways you could answer that.
Well, because if you look at recently, wasn't there a Swedish spacewalk, and they were going on about the fact that when you've got people in space, they have to wear these reflective spacesuits and things, because if they're in the full glare of the sun, then very quickly their body can heat up to boiling point. It can be 100 degrees, and on the dark side, in the shade, it's very, very cold because you're just radiating your heat straight away again. So I suppose it's quite a difficult question to answer, because if you're having sunlight hitting you, you're soaking up a lot of energy. If you're in the shadows, you're not.
Yeah, and you just need to think about airplanes, and you see the condensation freezing on the outside of the airplane way above the clouds, and you know we're out in space yet. So I think that is actually quite a tricky question to answer.
Thank you, Carolyn. That's Carolyn Crawford. Well, time now to do a bit of kitchen science, and we told you earlier that what we're going to show you how to do is to measure the speed of light, a really fundamental number, in your own house. And all you're going to need is a microwave and 4 slices of bread and some butter, it turns out, because Ben and Dave have enlisted the help of Claudia F. Stathiou and her microwave, and they're going to do this in her house. Hi, Ben.
Hello, welcome to Kitchen Science. I'd like to introduce you to my new friend Claudia.
Hello.
So then, Claudia, what year are you in at school?
I'm in year 10.
And what do you enjoy about school?
Meeting up my friends at lunchtime.
Not the lessons, then?
Not particularly, no.
Well, thank you ever so much for inviting us to your house. And I see you've even let Dave Ansell in. Hello, Dave.
Good evening.
Now, I can see that Dave's playing about with the microwave, so what are you going to cook for us, Dave?
I'm afraid all we're going to be cooking is some bread and some margarine. But it does mean that we can find out the speed of light.
And why would we need to know the speed of light?
First of all, because it's kind of cool, but it's actually a really fundamental property of the universe. It's the fastest anything can move at all, ever. And this is really important with communications, so what's quickest we get a message from here to New York, or even more importantly from here to Mars.
It's strange that you mention that, because we're having a space show today, and we've been talking a lot about light years and that sort of thing. Now, Claudia, do you know what a light year is?
Is a light year the distance it takes light to travel in a year?
Yeah, that's exactly it.
So how are we going to measure the speed of light today?
So what we've got here is a perfectly normal microwave, a plate, some margarine and a knife, and 4 or 5 slices of bread. Brown bread's slightly better than white because you can see what's going on better.
Do you need a special microwave to measure the speed of light?
Well, as long as it cooks, that's fine, because what we're actually going to measure is the speed of microwaves. Now, microwaves are a kind of electromagnetic radiation like radio waves or infrared light or light itself. And all of these travel exactly the same speed, the speed of light.
So how are we going to combine bread, butter, a microwave and a plate to do a physics experiment?
Well, the first thing we've got to do is stop the turntable on the microwave. So, Claudia, if you'd like to take the turntable out of the microwave and put a plate upside down in its place, that would be brilliant.
So Claudia's taken out all the bit that rotates from the microwave and just put a plate in there upside down. Why have we done that, Dave?
Well, inside a microwave you get lots of hot spots, and the turntable's there in order to move the food through those hot spots and average out the cooking on all the different bits, otherwise some bits would get overcooked and some bits undercooked.
So it's to make sure that your food cooks evenly while it's in the microwave?
Yep, and we want to measure where those hot spots are, so we don't want it to turn.
So we want it, in effect, to not cook it evenly?
Exactly. So now, Claudia, would you like to butter 4 slices of bread and lay them out evenly on the plate?
So Claudia's just spreading a bit of butter on there. Is there any particular way that you should butter it, Dave? Should it be a thin, even coating, a thick, lumpy coating?
You want it as even as possible, fairly thin, but you want to be able to make sure you can see the butter when it's there. And if you're going to try this at home, you want to get the butter all the way right to the edges of the bread.
OK, so that's all done. What do we do next?
So now you want to lay the 4 pieces of bread out very close to each other in a square. You might want to spread a little bit more butter in the joints between the bits of bread.
Okay. So it's a bit like using butter as polyfiller in the cracks?
A little bit, but not. You don't want very much, just a very light covering, just so it goes right to the edge.
OK, Dave, so what's next?
Claudia, if you'd like to put that plate in the microwave on top of the other plate. Beautiful.
So now in the microwave, basically, we have a raised plate that isn't going to turn, and it's just completely coated in bread with a thin layer of butter all the way across the top.
That's right. So now what we're going to do is we're going to cook that margarine until it just starts to melt and see where it starts to melt first.
So we're expecting this to only be for a few seconds, really?
Yeah, it's only about 10 or 12 seconds. So you probably want to keep stopping it and checking until it just starts to melt.
All right, then. Well, Claudia, do you want to put your microwave on?
OK.
Well, it doesn't seem to have done anything yet, Dave.
Bit more, maybe.
Well, there's a couple of melted patches.
Maybe a little bit more.
OK, and it's finished now. It's been about 15 seconds. Claudia, what does it look like?
There are 2 sort of spots where all the margarine's melted.
Well, the margarine seems to have melted in a patchy way. It's not all evenly melted. It almost looks like there's sort of lines in it. Should we expect to see a pattern?
Yeah, that's right. The bits where the margarine is melted, obviously getting hotter quicker. These are the hot spots.
So why do we get hot spots in a microwave?
Well, a microwave oven cooks with a kind of light called microwaves, which, as the name suggests, are a kind of wave. And the size of the microwave oven is very carefully chosen to produce a standing wave, which I can demonstrate with this skipping rope. And I want Claudia to hold the other end of the skipping rope. Now, what I'm going to do is wobble one end. If I get the speed right, it will start to wobble backwards and forwards and produce a really big swing. Now, if I speed it up a bit...
So Dave's standing about 3 metres away from Claudia, and he's sort of shaking this bit of rope around. It's not quite tight between them, but it's sort of wobbling about. I can see he's trying to get it to be exactly the right rhythm. Dave, it seems to have sort of settled into a shape now, really. You can see kind of an S shape in it.
Yeah, that's right. I don't know if you've ever done this at home before, but if you get the speed of it right, instead of the whole thing swinging backwards and forwards like a swing, the middle of it stays still, and there are 2 bits either side which wobble backwards and forwards like individual swings in opposite directions.
OK, so there are bits in the rope that effectively aren't moving at all, and the other bits are moving quite a long way.
Yes, that's right. Now, the reason is you've got a wave which travels down the rope from me to Claudia, and then that bounces off her hand and comes back again. Now, when we were getting an S shape, that was exactly one wavelength between me and Claudia.
So what do you mean by wavelength?
Well, if you've ever watched waves on a sea, it's the distance between 2 peaks on a wave.
So how does this bit of rope tell us anything about the microwave?
Just in the same way that the wave I'm sending down this piece of rope to Claudia bounces off Claudia, the microwaves going inside the microwave oven bounce off the far side of the oven and come back again. Now, this sets up a standing wave inside the oven, and the places where the microwaves are moving a lot, it transfers lots of energy into the food and it gets hot very quickly. And the places where they're not moving at all, it doesn't heat up at all.
Is it the bit where the wave isn't moving is where the margarine is left, but the bits where the wave is moving a lot, there is no margarine left?
Yes, at the high points in the standing wave, the margarine's all melted.
So what does these melted patches in our butter tell us about the speed of light?
The distance between 2 melted patches of margarine will be half the wavelength of a microwave. Now, there's 2 important things about a wave. One of them is its wavelength, which we've talked about already, and the other one is how fast it's vibrating. Now, if you look on the back of the microwave, it should tell us how fast it's vibrating. There should be a number on there measured in gigahertz. So, Claudia, if you'd like to have a look at the back of the microwave.
2,450 megahertz.
Brilliant.
That's great, Claudia. Come back. So 2,450 million hertz. Is that right, Dave?
Yeah, that means that the microwaves inside that oven are vibrating up and down 2,450 million times every second.
So what are we going to do now that we know the frequency?
So the other thing we need to know is the distance between 2 of these melted splodges. So, Claudia, if you'd like to find a ruler and measure the distance between 2 of them.
So Claudia's measuring between one of the lines of melted butter and the next one. About how far is it, Claudia?
About 6 centimetres.
That's pretty close, yeah.
OK, so now we know the frequency, and we know that half of the wavelength is 6 centimetres. Where do we go from here?
So the first thing we need to work out is what the whole wavelength is. So, Claudia, can you work that one out?
12.
Well done. So you've got a wave, travels 12 centimetres, 2,450 million times every second. So if we multiply 12 centimetres by 2,450 million, we should get a number pretty close to the speed of light.
OK then, Claudia, well, I can see you've got a calculator, so shall we work this out?
So it's 2,450 million times 12, which is 29,400 million centimetres per second.
Yes, that means we've measured it to move at about 294 million metres every second, which is actually an incredibly accurate answer. The actual answer is nearer 297 million metres per second, but that's pretty good going for a microwave and some bread.
Now, that sounds really, really fast to me, but I can't really get a grasp on what that is. Could you tell me in miles per hour?
It's about 660 million miles per hour.
Wow. So going back to what we were saying at the beginning of this about light years, if we know that it can do sort of 600 million miles per hour, how far is it going to go in a year?
So to turn it into a light year, all we need to know is how many hours there are in a year. So that's 24 hours in a day times 365 and a quarter days in a year, which comes out at about 8,760 hours in a year. Multiply that by 660 million, and we get about 6 million miles in a light year. So it would take you a while to drive there.
I think that's really impressive. I wouldn't want to sort of try and go to Mars or anywhere on my holiday. I think it would take just a tiny bit too long.
Fantastic. Well, thank you very much, Claudia, for inviting us into your house. Thank you once again, Dave, for showing me the speed of light. And thank you to you all for listening. That's it from Kitchen Science this week. So it's goodbye from Dave.
Goodbye.
It's goodbye from me, and it's goodbye from Claudia.
Goodbye.
Well, thanks, guys. That was Ben, Dave and Claudia finding out how to measure the speed of light in their own kitchen. And if you want to repeat that experiment, you can find out how to do that on our website at nakedscientist.com/kitchen science. And there's about 50 gazillion other fantastic experiments that you can do at home too, just on nakedscientist.com/kitchen science.
Sorting out the sparks from the quarks. The Naked Scientists.
Now, we're very pleased to welcome from the Space Telescope Science Institute in Washington, D.C., Dr. Maggie Turnbull. Hi, Maggie.
Hello.
Now, Maggie, you've come up with a short list of planets which are within the habitable zone of stars. In other words, just the right distance, so they're not too hot and not too cold away from that star, so they're what's called Goldilocks planets. Not too hot, not too cold. But how do you look for that kind of thing?
Well, it depends on what exactly you're looking for. If you want to actually try to detect the planets themselves, which is really the hard way to do it, then you have to build a space telescope that is able to somehow block out the light of the star, which is extremely bright, so that you can still see the very, very faint light coming from that tiny little planet. That's
People have come up with various ways to do that, haven't they, Maggie? I mean, there's some very nice petal-shaped star shade so that you can just blot out the sun and leave the planets around the outside. But other than that, are there any other ways to do it?
Well, the easier way to do it would be if that planet had some sort of intelligent civilization on it that was broadcasting its presence to the universe, and we could just listen for those signals, which is, of course, what the search for extraterrestrial intelligence scientists are trying to do. But that puts the burden of technology on them, so they have to outshine their star, at least at certain frequencies, so that we can see them.
Well, this seems like a good opportunity to talk to Tony, who's in Westcliff, because he wants to ask something about that. Hi, Tony.
Good evening, sir.
What's your question for Maggie?
Well, we've been sending out radio waves for about 80 years, give or take a little. And I just wondered, they'll go at the speed of light, so it'd be 80 light years, the nearest star that could hear them, wouldn't it?
Right.
Anyway, I just wondered how many planets come within that orbit, within that sort of range.
Right, so you can imagine this sphere around the Earth going out into space that is filled with radio noise that we have emitted because of our technological activities. And that, if you want to count the those very first broadcasts where people were just beginning to really play around with radios and transatlantic communications, for example, then we have that, the radius of that sphere around us is something, like 80 or maybe as much as 100 light years. And within that distance, I don't think in terms of light years. I'm an astronomer. I think in terms of parsecs. And 1 parsec is about 3 light years. So if you say the sphere is about 30 parsecs in radius, I know that there are about 3,000 to 5,000 stars inside that sphere around us. And of those, about, say, 2,000 of them are sun-like stars. Say 1,500 to 2,000 would be roughly I'm being generous when I say
like
sun-like.
our own star, Maggie.
Yeah, not exactly like ours, but enough like our star that they could live long enough and have planets that could have life on them that's somewhat similar to our own.
That's quite a lot, isn't it?
It's a lot, but if you also have to consider that not every single one of those stars is going to have planets, and of the ones that do, they're not all going to have Earth-sized planets that are in the habitable zone. So I would say that a reasonable number would be about 10% of those, and I would say anywhere from 1 to, say, as many as 500 habitable planets are within that sphere of noise that we've created. But you have to keep in mind that, most of the transmissions that are leaking out into space are doing just that. They're leaking. They're not beamed intentionally at any star system. So they're very weak by the time they get there. And they're not all the signals that we leak out into space are not going equally in all directions. Sometimes you have to be in a certain spot to be able to pick that up.
Great question, Tony. Thank you very much. So, carrying on with that sort of theme, Maggie, how do we try and pick up alien signals, assuming that people are technologically ahead of us and they are sending things our way? How do we try and find them?
Well, we have to listen. And getting time on a large enough telescope to be able to detect transmissions of the type that we are actively leaking out into space is actually kind of a challenge. So SETI, as a scientific effort, as a pursuit, as something that the astronomical community and public are engaged in, is really just a very limited activity right now. And I think that one of the most exciting things that will be happening soon with regard to SETI is the construction of the Allen Telescope Array in Northern California. And that is underway, and actually part of it is functional now. But when it's completed, that will really be our first opportunity to begin monitoring the skies 24/7 for intelligent signals coming from other star systems.
You have narrowed down the number of planets that you think fairly locally might play home to foreign life. How have you done that, and how many of them are there?
I have attempted to do this exercise by picking out stars that are similar to the Sun with regard to a lot of different factors. Like, for example, we don't want to spend our telescope time looking at stars that are really young, because those systems are probably still filled with the debris of planet formation, and you've got huge collisions going on with comets and asteroids, and those planets just are not very nice places to live right now. No way do they have radio telescopes. And so we don't want to look at the really young ones. On the other hand, really old stars tend to not have a lot of the heavy metals like iron and nickel that are needed in order to form planetary, at least terrestrial planets. So really old stars, or stars that just don't have a lot of those metals in them, are not good places to look either, because they're not likely to have planets like the Earth.
So what does that leave you with?
Well, we end up with actually a pretty substantial chunk of stars. And I have a list of on the order of 18,000 stars for us that are really our top targets for SETI. They're stars that I would go to. What do you think?
Are they anywhere near here?
Yeah, we have some of them are very nearby, and I think a lot of people know of, for example, Alpha Centauri I'm just naming a few. I'm not saying that these are the best places
This
in
is
the
where you'll
entire
find
universe.
UFOs.
Okay? Do not put me on the spot like that, because I am not going to tell you what's the best one to look at. But for example, Alpha Centauri is a sun-like star. It's the closest sun-like star to us. It's only 1 parsec away, about 4 light years. And it actually is in a triple star system, but maybe it could still be habitable to Earth. The second star actually gets a little closer than I'd like it to, so it's not ideal, but it's interesting because it's so nearby and it's so much like the sun. And then Epsilon Eridani is another bright star that is actually a little bit less luminous than the sun. It's kind of an orange star. It's a little cooler. So planets that are habitable would be a little closer to that star than they are in our solar system. But that's actually one of my very favorite stars that I feel like we absolutely must look at.
OK, well, I've got loads of emails here, which are actually for both you and Carolyn, so we might as well have a look at those. We've got one cheeky question from Simba, who says, Maggie, can you tell us in miles an hour how fast does the Earth travel around the Sun? But you're not going to answer that because, of course, that's our question for this evening, which Helen's going to answer shortly.
Well, I do have a question about that, though. Do you guys really think in terms of miles per hour? I thought British people thought in terms of kilometers.
Of course, it's America, two great nations, America and the UK. We still know how to drive. Obviously, we know how to drive on the right side of the road. You're on the wrong side of the road, but we still use the right distance measurement, which is miles. But Carolyn, got a question here, which is, this is from Mark, and he says, really enjoying listening to your show. My questions are, do all stars belong to a galaxy, or are there some stars which are orphans? What do you think of that one?
Well, certainly all the stars we know about do form in a galaxy. I mean, to be quite honest, we're going to have a hard time finding solitary stars that aren't in a galaxy. They'll just be very difficult to find. It is true that it's possible that stars can leave a galaxy. Sometimes galaxies collide, and as part of this process, when they merge, they throw out lots of stars out in the vastness of space. So there may well be lots of orphan stars out there, but again, we're not really going to know about it. So most of the stars we know about, yes, they're in galaxies.
I've got a question here from Richard in Bury St Edmunds that's just been emailed in, and he says, what if we term our universe, if what we term our universe was created by the Big Bang? Does this mean the whole universe was a massive star that has exploded? And could this star be just part of a small part of an even bigger universe that we don't know about as yet?
Well, anything's really possible. It's unlikely to be a star as we understand it, because stars don't happen till hundreds of thousands of years after the Big Bang. But there's always this idea that maybe our universe is just part of another universe, and maybe there are other universes out there. But to be quite honest, that's getting to philosophy. We're never really going to know the answers to those. Well, not at the minute, anyway.
Maggie, have you got an opinion on that?
Whether or not our universe could be a sub-universe of an even bigger universe?
We like to probe the hard questions here on The Naked Scientist. All right, what do you think of this one, Maggie? It's from Keith McNichols, who says, I've been listening to your podcast for a little while now. I've got a question which has been bothering me for some time. Why is north usually considered up? This is a point of contention with me. In protest, I keep my globe so the south is on the top.
You can keep your globe however you want.
Carolyn, any strong feelings?
I don't think north is considered up. I mean, you can go into colonial history if you want. I don't think there's a right or a wrong way. So keep your globe which way you like.
But if we look at how the planetary system did actually form, lots of people don't realise that, of course, all the planets in our solar system are on a flat plane, aren't they?
That's right.
And that stems from how they, in fact, formed from this initial protoplanetary soup, which was a sort of disk around the star.
Yeah, which was rotating round, yes.
So how did they end up with that disk turning into all these individual planets and the positions they've got? Do we know?
Well, it's all the stuff that's left over from, the star formation. But of course, you've got to remember what we were saying earlier, solid rocky planets, they form closer in, and much more sort of lighter gassy objects form much further out. So that really is what, it's certain planets can only form certain distances from the star. So that's kind of what determines what planets form where.
Thanks, Carolyn. Now, we're almost out of time, which means it's time to find out, actually, A, who's won, and B, what the correct answer is to how fast does the Earth go zipping round our solar system around the Sun. Helen?
Well, we've had a huge bumper crop of answers for our teaser question this week, so thank you to everyone who phoned in, who emailed in. But we had to have just one winner, and that is Chris from Poland. Not Chris in the studio.
I'm not in Poland.
But he has been listening to our podcast and is actually listening today live on the BBC website.
Dzień dobry.
Which is fantastic. Thank you so much for that. And the answer is, round about 70,000 miles per hour. And I'll just go through how we work that out so you've got a bit of an idea of how we got there. But roughly what we're talking about is speed being distance divided by time. So if we think of the time we've got is a year, which is roughly 350 days, or, OK, let's say 25 hours in a day, which is 8,750 hours, roughly. And the average distance that the Earth is from the Sun is about 100 million miles. So if you think about it, the Earth has to travel in a great big circle all the way around the Sun, which, if you know your I was going to say trigonometry. What's
your
the
maths.
word? Your maths. If you know your maths, it's roughly 2 times that magic number pi, which is a roughly 3 times that 100 million miles, and you're going to come up with roughly 680 million miles, which is how far the Earth travels in that year, which is that 8,750 hours. And if you've got a calculator or a very good brain and you can work that out, it's around 72,000 miles an hour. Some of you are coming in with slightly less, coming in with sort of 30 kilometres per second and 18 miles per second, I think, or something like that. But basically, it's very fast indeed. And Chris in Poland is our winner. Thank you so much.
Thanks, Helen. And yes, it is pretty fast. And 30 kilometres per second is actually the correct second answer.
That's right, in seconds. So it is
stupendous distance in 1 second, 30 kilometres.
I'm surprised our heads don't just fall off from going
If the planet
so
stopped
fast.
suddenly, I think they probably would do. But anyway, that's it for this week. A massive thank you to our wonderful production team here at The Naked Scientist. Thank you to Helen for helping to present this week's show. Thank you to Petro, who handled the phones, to Ben Vausler, who put together our kitchen science, Dave Ansell and Azzy Katiri. Next time, we're going to be coming back down to Earth, thankfully not with a bump, and that's because we're going to be looking all about the science of animal behaviour. We'll have Tim Clutton-Brock from Cambridge University to tell us about meerkats and why they have such a rich social life. We'll also be hearing from Andrew Smith, who will tell us about how monkeys choose a bed for a night and why they choose the colour of the fruit that they prefer to eat. And Nikki Clayton will be here to tell us about some really clever birds called scrub jays that can plan for the future based on experiences they've had before. Don't forget as well that we're going to be launching Question of the Week next week, so if you want to know what's in store for that, then you can have a go at Sabina's question, which was if you drilled a hole right through the middle of the Earth and dropped a ball down it, what would happen? If you think you know the answer to that, it's Question of the Week at nakedscientist.com if you'd like to have a go. And in the meantime, let me say thank you to the people who contributed this week, to our guests Terry Herford, Carolyn Crawford, and Maggie Turnbull. For more science in the meantime, our forum, nakedscientist.com/forum. That's a thriving hubbub of scientific mystery, intrigue and discussion. It's just waiting for your input. Please take a look, nakedscientist.com/forum. Have a great week. Thank you for joining us. Please send any questions in the meantime to chris@thenakedscientists.com. We love hearing from you, so do please write. Until next time, goodbye.